Hey guys, my name is IBM and it was a boring morning, so I decided to do some physics and solve the May-June papers. So today I'm going to solve May-June 2024 papers, and I'm starting with question paper 2-1. That is May-June 2024. This is AS level structured equations, the May-June 2024 series. So here I have the question papers. I'll solve this. I'll solve 2-1. This is May June 2-1. It's May June 2-1. Two. I'll also solve 2-2. This is May June paper 2-2. You can see it is 2-2. I'll also solve 2-3. So this is May June. I think this is 2-3. Yes, this is May June paper 2-3. So the papers are strictly different, so you don't expect them to be the same. Unlike paper 4s, which are different, paper 2s are sometimes completely different. So without wasting time, let's start with the 2-1. So I will not read through the instructions. They are the usual instructions. I will not go through the data. It's the usual data you already see. I will not go through the formula. It's the usual formula you already see. So I'll go straight to the first question. So the drag force Fd acting on an object falling through air is given by this equation here, where A is the cross-sectional area, V is the velocity, rho is density, C is a constant called the drag coefficient. Use SI base units to show that the drag coefficient has no units. So if you're a teacher, I always encourage you to teach your students to lay out their work systematically. This is normally what I do when I teach this part to year 12 students or AS students. So the quantity whose units are required is always made the subject to make your work look systematic. So we want C to be the subject, so I'll make C the subject. So making C the subject, I have that C is equal to twice the drag force, then times or divide by in the denominator I have density, I have area, I have v squared. So I've made C the subject. So I also encourage you to tell your students to list down the units for each of the quantities. So remember, A was the cross-sectional area, which is measured in meters squared. Then V was velocity, which is meters per second. And then rho was density. Density is kilograms per meters cubed. And then Fd, which is the drag force, is, of course, force is mass times acceleration, where mass is kilograms and acceleration is meters per second squared. So those are the units for the drag force. So it means the units for C would be, I will ignore the coefficient 2 when finding the units, so it will be kilogram meters per second squared for the drag force, divided by for the density, which is kilogram meters per minus 3, then times for the area, which is meters squared. Now note that the velocity is squared, so I have to square the units for velocity, so this will be times meters per second, but this should be squared. So encourage your students to always simplify quantities until all the units cancel out or all the units match. So it means I'll simplify this. When I put equal signs here, it means I'm now simplifying. So this will be kilograms meters per second squared divided by kilograms. So meters per minus 3 times meters squared times meters squared, because this square squares everything in the brackets. So I'll have meters per minus 3 times meters squared times meters squared. So we sum up the powers. So we have minus 3 plus 2 plus 1, which becomes m per 1. So this will be simply kilograms times meters. Then s power minus 1 is again squared, so it becomes s power minus 2. So what happens is that I'll cancel out each of the corresponding terms. For instance, kilogram cancels out, m cancels out, per second cancels out. So now I just write a conclusion. So that this means that C has no what? No units. If you're a teacher, discourage your students from putting equals to 1. It's really wrong to say that the units equal to 1. That is a contradiction. Then part B, figure shows a sphere falling at terminal velocity. Of course, at terminal velocity, there is constant velocity. It means the resultant force equals to 0, which means the acceleration is also equal to 0. So assume that the upthrust on the sphere is negligible. So the upthrust force is approximately equal to 0. On the figure, draw and label arrows to show the directions of the two forces acting on the sphere. So since the upthrust is already negligible, so I'll only put the weight, which acts vertically downwards, and I'll put the drag force. Because the upthrust has been considered negligible, so I'll just consider the drag force, which is the force due to air resistance. So I'll put here the drag force. Drag force, or you can call the viscous force. Or I think there is no E on the word viscous. So this is going to be the viscous force. Okay. So those are the two marks. The mass of the sphere is 49 grams. Calculate the drag force Fd acting on the sphere. So remember, it is moving at terminal velocity. So I'll simply say at terminal velocity, the resultant force should be equal to 0. That means the weight downwards should be equal to the drag force. So this implies that the weight downwards is going to be equal to the drag force Fd. So the drag force Fd is going to be equal to mg because the weight is mg. So I'll just substitute. The mass is in grams, so I'll say times 10 to the power of minus 3 to change it to kilograms. So this will be 49 times 10 to the power of minus 3 to change it to kilograms. Then times g, which is 9.81. At your level of AS, I don't expect a student to use 10 for g. So I'll check with my calculator. 49 exponent minus 3, then times 9.81. So this is giving me 0.48. Avoid writing answers to less than two significant figures unless it is an absolute uncertainty. So this is going to be 0.48, maybe 1 if you want, or you can just write 0.48 to two significant figures, newtons as the drag force. The sphere is falling in air at a terminal velocity of 25 in SI base units. Of course, the units is meters per second. The density of the air is 1.2 in SI base units. The diameter of the sphere is 0.06 in SI base units. Use your answer in C to calculate the drag coefficient C for the sphere. Remember from the previous equation, we have already seen that the drag force was given as a half times C times rho times cross-sectional area times V squared. But we have got the drag force as 0.48. And remember, A was not the area of the sphere, it was cross-section area. If you draw a sphere, the cross-section through a sphere is a circular disk. So it means the area is going to be the area of a circle. So the drag force Fd is 0.4, and the area is going to be the cross-section. The cross-sectional area is the area of a circular disk, so it is the area of a circle. So the area A is going to be pi r squared. It will not be 4 pi r squared. That is, it's not going to be the area of a sphere, but to be the area of a circular disk, because A was not area of a sphere, but was cross-sectional area. And the cross-sectional area of a sphere is a circular disk. So because they have given us diameter, I'll just modify this. Where there is radius, I'll put diameter. So this will be pi d squared divided by 4. If you want, you can divide the diameter by 2 and use area as you use r as 0.03 directly, which is still fine. So I'm now going to just substitute in the formula. So the drag force is 0.48. You could use 0.481, which is equal to a half times c. Remember, we want to find the c, so I'll put times c here. The density of air is 1.2. The area is going to be pi times d, which is 0.060 squared divided by 4. So this is the area. Then times v, which is 25. So I'm just going to press my calculator. I don't always want to make the subject at this level, but I'll make c the subject then. So c is going to be 0.48. I'll bring in the 2, which is in the denominator, this 2 here. There is a 4 in the denominator here, so I'll say times 4, then divide by. In the numerator, I remain with 1.2 times, I have 25 times pi times 0.060 squared. Okay, so let me just check my calculator. 0.48 times 2 times 4. So I'm going to divide this by open brackets. 1.2 times 25 times pi times 0.06 squared. So I'm getting as, no, I have to check this again. I think I left out v was squared. This is squared. So this is going to be squared, okay. So I'll just again divide this by 25, which gives me 0.45. I can repeat this again. Let me check. So I have 0.48 times 2 times 4 divided by open brackets 1.2 times 25 squared times pi times 0.06, but this is squared. Okay, it is 0.453 or 0.45. So I'll just write two significant figures. So this will be 0.45. Of course, here we have already said it had no units in the previous part, in part 1, part A, so I don't need to mind about the units. So C is 0.45. Okay, that was a very easy question. So define velocity. We know that velocity is the rate of change of displacement, that is the change in displacement over time. So I can simply say the velocity is the rate of change of displacement. Now, many times students who are struggling with the English language will say rate of change of displacement per unit time. That means again they are dividing this by time, so time cancels out. So you can't say rate of change of displacement per unit time. You cancel out the rate because rate means something divided by time. So if you're not very sure of the language, you can simply say displacement is changing this. Velocity is changing displacement over time taken. Change in displacement divided by, this is allowed, time taken, that is velocity. A student throws a ball over a vertical wall of height h, as shown in the figure. The ball leaves the hand of the student at a height of 1.2 meters above the horizontal ground. So let me try to prolong this until I reach the wall. So this height, this distance here is 1.2 meters. The ball has an initial velocity of 22 meters per second at an angle of 40 degrees. So we have to resolve this velocity into two parts. Its component in the horizontal will be 22 cos of 40 or 22 sine of 50. Its component in the vertical, because it has two components, its component in the vertical, initial velocity in the vertical is going to be 22 sine of 40 when we resolve it in the vertical. The ball is with, the ball is, the wall is a horizontal distance of 36 meters from where the student releases the ball. Air resistance is negligible, which means the equations of motion can be used since the acceleration of course, in the horizontal acceleration is 0. The acceleration in the vertical is going to be the acceleration due to gravity, which is going to be, since it initially goes up, so it is going to be negative g. That is negative 9.81. When I put subscript x, I mean in the horizontal. When I put subscript y, I mean in the vertical. So here it is going to be negative 9.81 meters per second squared, acceleration in the vertical. Determine the time taken for the ball to reach the wall. Because time is a scalar, whichever direction I consider, if I consider horizontal motion or vertical motion, the time is going to be the same. So I will consider horizontal motion because I have the horizontal distance. I don't know the vertical distance. So I will say considering horizontal motion, and I'm going to use S in the horizontal equals to initial velocity in the horizontal times t plus a half acceleration in the horizontal times t squared. That is the equation of motion. But remember, I've just said acceleration in the horizontal is 0 because there is no force acting in the horizontal. If there is no air resistance, then the only force acting on the body is in the vertical, so which is the weight. So acceleration in the horizontal will be 0, so the velocity remains constant in the horizontal. So if that is the case, then this part here becomes 0. So S in the horizontal is being given as 36. Initial velocity in the horizontal, we have resolved 22 in the horizontal and it was 22 cos of 40. Then we multiply this by t. So it means t is going to be 36 divided by 22 cos of 40. So 36 divided by 22 cos of 40. So this is giving me 2.14. So this is 2.14, or I can just write two significant figures such as 2.1. So I'll say t is 2.1. So the examiners will decide on the tolerance if I think this, but 2.1 would be correct, or 2.14, I think 2.14 seconds. So that is the time taken. Then calculate the vertical component u of the initial velocity of the ball. Now we want the vertical component, we just resolve in the vertical. So initial velocity in the vertical is going to be 22 sine of 40, or it can be 22 sine of cos of 50. 22 sine of 40, or you can say 22 cos of 50. After all, sine 40 is the same as cos 50. Why do I use cos? Because if you consider this angle here, this is 50 degrees. So when I take 22 to the vertical using 50, it will be 22 cos. So what is that answer? 22 sine of 40. That is 14. You can check with the cos, but I'm very sure it is the same thing. So this is going to be 14 meters per second. Since it is two significant figures, I don't need to worry about anything. The ball just goes over the wall. Calculate the height h of the wall. Okay, so the height h of the wall is going to be this distance 1.2 plus this distance here. So I'm going to find this distance. Let me call it sy. That is displaced s, the vertical. So h is going to be 1.2 plus s in the vertical. So to find s in the vertical, I'll use s in the vertical equals to initial velocity in the vertical, which is u in the vertical times t plus half acceleration in the vertical times t squared. Remember, acceleration in the vertical, because it goes above the point of projection, the acceleration was negative g, or negative 9.81. So s in the vertical is going to be initial velocity in the vertical. We have already got it as 14. We don't need to resolve again. Then the time, we calculated the time was 2.1. Of course, time is a scalar, so the time in the vertical is the same as the time in the horizontal. So 2.1. So here, remember, I've considered vertical motion. That is motion in the vertical. Then so this will be plus a half, but the acceleration is negative. So plus a half of negative 9.81, then times 2.1, but this is squared. So I'll just press my calculator, or I can simplify this to have 14 times 2.1 plus and minus becomes minus 0.5 times 9.81 times 2.1 squared. So I'll say 14 times 2.1 minus open bracket 0.5 times 9.81 times 2.1 squared. So this is giving me 7.7 7 points. Let me just round off to two significant figures. So it will be 7.8. So s in the vertical is going to be 7.8 meters. But remember, we said h is 1.2 plus 7.8, which when you combine, you get 9.0. So h is going to be 9.0, or a value which is very close to 9.0, depending on how you round off. Depending on how you round off your value of t, depending on how you round off your value of s in the vertical, your answer will be very close to 9.0 meters. The tolerance, I think the tolerance can be determined by the examiners while marking. Then state the principle of conservation of momentum. That is question number 3. We normally state this principle wrongly. For those of you who have been watching my videos, these papers must have been the simplest papers you have ever seen, because they are almost a repeat of the questions done in the past. So the easiest way to state the principle of conservation of momentum is that the total momentum of an isolated system of interacting bodies is always constant. When I talk about an isolated system of interacting bodies, I'm referring to a system where there is no resultant external force acting on the bodies. So that is the easiest way to state the principle of conservation of momentum. Now, wrongly, people say total momentum is conserved. That one will not give you 2 marks. Alternatively, if you're not good at stating such a statement, you could say the sum or the total momentum of a system is constant if no resultant force, external force acts. So the total momentum of a system is constant if no resultant external force if no resultant external force acts. So of course, if there is no resultant external force, then the system is considered to be isolated. Instead of using the word isolated, I would use closed. A system on which there is no resultant external force is considered to be closed or isolated. Okay, an object of mass 2m is traveling at a speed of 5 meters per second in a straight line. It collides with an object of mass 3m, which is initially stationary as shown in the figure. So this is initially stationary, so initial velocity here is 0. After the collision, the object of mass 2m moves with a velocity v at an angle of 30 degrees to its original direction of motion. The object of mass 3m moves with a velocity w also at an angle 30 as shown in the figure. You must have seen this in my most of my videos, which are in the topic of, I think that is the topic of dynamics. You must have seen this. If you haven't seen this and you want to practice this, you can look for dynamics among the playlists. By considering the conservation of momentum in 2 dimensions, that is, we have the vertical and the horizontal. Calculate the magnitude of V and W. Okay, so I'll start with let me start with horizontal or along the direction of motion. So I'll say along the initial direction of motion initially. In the horizontal, remember initially it is only the mass of 2m which was moving, so the mass of 3m, its momentum is 0. So I'll say initially. In the horizontal, we have, remember momentum, I have to write a formula somewhere. Momentum is mass times velocity. So along the initial direction of motion, initially we have 2m, its speed is 5. Then plus, the other one was 3m, its speed was 0 because it was at rest. Then after collision in the horizontal, I have to resolve the velocity v in this direction. So we have v cos of 30. I also have to resolve w in the same direction. We also have w cos of 30. They will point in the same direction. So it means the total momentum after collision in the horizontal will be 2m times v cos of 30 plus 3m times w cos of 30. So that's total momentum after collision in the horizontal. So I have here 2m times v cos of 30, that is for the mass of 2m plus 3m times w cos of 30. So precisely when I simplify this, I have 10 times m equals to, I will have 2m v cos 30 plus 3m w cos 30. So 2m v cos 30 plus 3m w cos of 30. Of course, if you want, you can cancel out m. So this is along the initial direction of motion. Then I'll say perpendicular to the direction of motion. So I'll say perpendicular to the initial direction. Perpendicular to the initial direction of motion. So I now have to resolve the velocities in the vertical. So I come here, w in the vertical point downwards, and it will be w sine. If it was cos in the horizontal, it will be sine 30 in the vertical and points downwards. Then v in the vertical point upwards, and it will be v sine of 30. So the momentum upwards is going to be 2m times v sine 30, and the momentum downwards is going to be 3m times w sine 30. But remember, initially the body was only moving in the horizontal. So it means Initial velocity in the perpendicular was 0. I mean, initial momentum in the vertical was 0 for both. So it was 0. This should be equal to velocity for 2m is upwards. So I will say upwards is positive. So 2m times v sine of 30 plus. The other one is downwards. So if upwards is positive, then downwards should be negative. So it's plus negative 3m times w sine of 30. And when I simplify this, m cancels, sine cancels. So I remain with the fact that 2, no, let me leave there m so that I will easily substitute. So I will say 2mv is equal to 3mw. I've only cancelled out sine 30. So I'm now going to substitute 2mv into this equation here. So this is therefore going to imply that 10m is going to be, where there is 2mv, I'm going to put 3mw. So this is going to be 3mw. I'm removing this. 3mw cos of 30 plus 3mw cos of 30. So whatever way you use to solve this, m has cancelled out because it's a common factor. But I have that 10 is equal to, I think that is 6w cos of 30. So what is w? So it means w is going to be equal to 10 divided by 6 cos of 30. So 10 divided by 6 cos 30. So this is 1.92. So w is 1.92. But also remember 2mv is equal to 3mw. Also 2mv is equal to 3mw, where m cancels. So it means v is equal to 3w divided by 2, which will be 3 times 1.92 divided by 2. So I'll just multiply the answer by 3. Then I divide this by 2. So this is giving me 2.89. So my answers are going to be V, which is 2.89. Then W, which will be 1.92. Okay. The examiner can always decide the tolerance, the degree of tolerance to the answers, the range. Then an object of mass 4.2 kilograms is traveling in a straight line at a speed of 6 meters per second. The object is brought to rest. That means the final velocity goes to 0 in a distance of 0.05 meters by a constant force. The force is constant, means the acceleration is also constant. And always remember that if the acceleration is constant, equations of motion can always work. Calculate the magnitude of this force. So there are several ways of doing this. I'll use the simplest, which is conservation of energy. As it is brought to rest, it loses kinetic energy. So it means the loss in kinetic energy is going to be equal to the work done in bringing the object to rest. Remember, work done is equal to force times distance. So because I want the magnitude of the force, so the loss in kinetic energy is equal to the work done in bringing the object to rest. So the loss in kinetic energy is going to be a half m. The change, this will be change in v squared, is going to be equal to the force times the distance in the direction of the force. So this is a half. The mass is 4.2. Then let's say I'll just start with the initial velocity. So I'll say v squared. The change in v squared is going to be 6 squared minus 0 squared, or 0 squared minus 6 squared, whichever you consider. The negative does not The negative just shows that the force is acting in the opposite direction to motion. So this is going to be called the force F times the distance, which is 0.050. So I'll just press my calculator. A half, which is 0.5 times 4.2, then times 6 squared. Then I will divide this by 0.05. So I'm getting the force as 1512. So F is 1512 newtons, which is approximately 1500 newtons. So I'm very certain that this force would be 1500 newtons. That's method one. Alternatively, I can use equations of motion. Let me try equations of motion. So I know that v squared is equal to u squared plus 2as. So final velocity is 0 squared. Initial velocity is 6.0 squared. Then plus 2 times the acceleration. The displacement was, I think, 0.05. So I'm trying to find the acceleration. So the acceleration will be negative 6.0 squared divided by 2 times 0.05. So what is this acceleration? Of course, it's going to be negative 6 squared divided by 2 times 0.05. That is 360, but remember it is negative. So I'll say this is 360 meters per second squared, but remember it is negative. Okay, so that is the acceleration. So remember force equals to resultant force is mass times acceleration. I'll just ignore the negative. The negative just shows it is actually deceleration. So this is going to be 4.2 times 360, which I think should give us the same thing. 4.2 times 360. It is exactly the same thing. 1512 newtons. You could also use this acceleration to find the time, and then use the definition of force as the rate of change of momentum. But these ones are enough methods. Define strain. Of course, we know that strain, without struggling writing a lot of things, strain is the extension over original length. So I can just write a formula: extension divided by original length. Extension divided by original length, that is strain. Don't write a lot of things about strain or stress. A copper wire of length 4 meters has a uniform cross-sectional area 4.5 times 10 to the power of minus 7. The tensile force is 18 newtons. Tensile force of 18 newtons applied to the wire. This causes the wire to extend by 1.4. So this is extension 1.4. Remember to change this to 10 to the power of minus 3. To change it to meters. Up to its proportionality limit. So the proportionality limit is after an extension of 1.4 caused by 18 newtons. Actually, the Young modulus. Okay. So the Young modulus, normally my students use capital E for Young modulus, equals to the stress over strain. Or you can write stress is normally written by that, sigma over strain, which is epsilon. Of course, this is the force over area divided by extension over the original length. Or you can write F over area times the reciprocal, which is original length, over extension. So in other words, the Young modulus is actually force over area times. So the force is 18 over the area, which is 4.5 times 10 to the power of minus 7, then times the original length, which is 4.0, over the extension, which is 1.4 times 10 to the power of minus 3. So I'll just press my calculator. I'll press the numerators first. 18 times 4 divided by 4.5 exponent minus 7 divided by 1.4 exponent minus 3. So I'm getting 1.14 times 10 to the power of 11, or 1.1 if you want. You can write 1.1 times 10 to the power of 11. So the Young modulus is 1.14 times 10 to the power of 11 in pascals. So I'll just write here 1.14 times 10 to the power of 11. On the figure 4.1, draw a line to show how the stress varies with the strain for the wire up to its limit of proportionality. Of course, up to its limit of proportionality, the stress must be directly proportional to the strain. So it should be a straight line. So we can first find the stress. Stress is force over area. And remember, the force was 18, the area was 4.5 times 10 to the power of negative 7. So what is the stress corresponding to that strain? Let me just press my calculator here. 18 divided by 4.5 exponent minus 7. So this is 4 times 10 to the power of 367. So this is 4.0 times 10 to the power of 7 pascals. That is the stress. What is the corresponding strain? Strain is extension over original length. The extension was given as 1.4 times 10 to the power of minus 3. The original length was 4. Let me check. 1.4 exponent minus 3 divided by 4. That is 3.5 times 10 to the power of minus 4. 3.5 times 10 to the power of minus 4. Because it's a straight line, so the points I'll just consider as 0, 0. And I'll consider here they have given us the power of 7. And here they have given us the power of 4. So I'll have the another point will be 3.5 and 4.0. Of course, this is times 10 to the power of minus 4. This was times 10 to the power of 7. So those are the points I'm plotting. So 3.5 and 4.0, I think it is here. This must be the point. So I'll just draw a straight line which stops up to, it should be stopping at 3.5 and 4, because the stress is on the vertical, so the point is going to be here. I think I need to, no, I don't need to increase the thickness. Yeah, so that will be my graph. Stress is directly proportional to the to strain, so it will be a straight line. And the proportionality limit is going to be at that point. So I will stop at 3.5. This is 3.5 against 4. A second copper wire has the same length. So original length is the same. But what was the first one? The first one was also copper. So it is copper, copper. So Young modulus is the same. E is the same. But a larger diameter. So diameter is now larger. Both wires are subject to the tensile force. So the force is the same. By placing a tick in each row, complete the table to compare the stress and strain of the two wires. Remember, we have seen Young modulus is force over area times original length over extension, that is multiplication. So The Young modulus is the same. The force is the same. Our original length is the same, but larger diameter. So let's first look at the first part of stress. Stress is force over area. So the diameter is larger, so it means the area is greater, because area depends on the diameter. So the area is greater for the second wire, and stress is inversely proportional to the area. So because the area is greater, the stress is smaller. So for the second wire, the stress is going to be less. That's less. It can't be the same. Then let's check the strain. Both wires are subject to a tensile force of 18 newtons, so the force is still 18 newtons. So we want to check the strain, so I'll just use a simple formula that strain is equal to Young modulus times the stress. The Young modulus is a constant, but the stress has decreased. Because strain is directly proportional to stress, a decrease in stress will mean a decrease in strain. So this also will be less. So the second wire will have a less stress and therefore less strain, because stress and strain are directly proportional. So the answers must be those two boxes. A stretched string PQ has length 1.2 meters. One end of the string is attached to a vibration generator and the other end is attached to a wall, as shown in the figure. Okay. So we expect a progressive wave to leave the vibrator to reach the wall, and it must be reflected. The vibration generator is switched on and a stationary wave is formed on the string. The string is shown at one instant of time in the figure 5.2. Explain how a stationary wave is formed between the vibration generator and the wall. Of course, this is very easy. We expect that a progressive wave from a vibrating generator travels along the string. So I will say a progressive wave from the vibration generator travels along the string and is reflected at the fixed point on the wall, and is reflected at the fixed point on the wall. A progressive wave from the vibration generator travels along the string and is reflected at the fixed point on the wall. Of course, it means the incident and reflected waves are going to be identical, same speed, same frequencies, and therefore, but they are moving in opposite directions, so they will superpose. So the incident and reflected waves superpose to form a stationary wave. The incident, which is coming from P, and reflected, which is coming from the wall, superpose. They superpose to form a stationary wave. So the incident and reflected waves superpose to form a stationary wave. Of course, the principle of superposition applies here. Then calculate the wavelength of the stationary wave shown in the figure. Let's see what is shown here. So we have 1.5 cycles. The length given there, which is 1.2, the distance between P and Q, which is 1.2, is forming 1.5 cycles. So this is a half, and a half, 1.5 cycles. So 1.5 cycles, I think that is 3/2. So the length, which is 1.2, is giving us 1.5 cycles, which is 3/2 of the wavelength. So which means the wavelength is going to be equal to 1.2 times 2 divided by 3. So this is 1.2 times 2 divided by 3, which is 0.8. So I'll write 0.80. So I can write 0.8 because it's exact, but if you want to get used to writing two significant figures, 0.80 meters. The figure 5.3 shows stationary wave at time t equals to 0 when all points on the wave are at their maximum displacement. So all points are at their maximum displacement at t equals to 0. So it means after a quarter a cycle, it must be destructive. After another quarter, it must be again constructive but reversed. That means after half a cycle, it should be another complete. It should be half a cycle on one side and half a cycle on the other side, which gives us a complete cycle out of step. But this will be a reversed phase. So let's see the question. The period of the wave is 0.14. On the figure, sketch the shape of the stationary wave at t equals 0.24. So what is 0.24? So if t equals to 0.24 seconds, this is the same as 0.16 seconds plus 0.8 seconds. Is it 0.8 or 0.08? 0.08 seconds. So this is one complete cycle and a half a cycle. So I'll just ignore the one complete cycle and concentrate on half a cycle apart. So it means after 0.8 seconds, it means if there's a progressive wave which is moving to the left, it will have moved half of its cycle. And if there's a reflected wave which is the progressive wave moving to the right will have moved half of its cycle. And a progressive wave moving to the left, which is a reflected wave, will also have moved half a cycle. So it means that half a cycle to the left and another half a cycle to the right. This means we have a complete cycle apart, which means what went as, or if at t equals 0, we have particles at maximum displacement, as shown in the figure. It also means that t equals 0.24 seconds, we also have the particles vibrating at maximum displacement, but in a reversed manner. So it means we shall have something like this. So I have to ensure that, of course, the amplitude of vibration is the same. I need to be very careful with this. Let me try to use a ruler to ensure that the amplitude of vibration is the same. So my graph should not go beyond this point. So I'll have something like this. Okay, so that is after 0.24 seconds. I just looked at the last part, which is half a cycle. If two waves are half a cycle, one wave moves half of its cycle to the left, another one moves half of its cycle to the right. It means the time out of step is a full cycle. So it means we shall again have constructive interference because the phase difference will be 360 into half to the left and another half to the right. The difference is one full cycle. So divide by wavelength, that means we have 360 degrees, which is constructive interference again. But this time it will be reversed. Then our points R and T on the string are a horizontal distance of 0.3 meters apart and in positions shown in the figure. State the phase difference between the oscillations of points R and T. Remember, this is a stationary wave, so do not forget this. This is a stationary wave, so I will draw a horizontal line through this. So this is one segment, and this is the neighboring segment. And remember, your teacher must have told that particles in two adjacent segments vibrate 180 degrees out of phase. Particles in the same segment vibrate in phase. If R and T were in the same segment here, the phase difference would be 0. But since they are in two neighboring segments, they are 180 degrees out of phase without even calculation. So this is 180 degrees out of phase, or pi radians. But they want the answer in degrees, but I don't think writing radians would be wrong. So it is 180 degrees or pi radians. Then calculate the speed of the progressive waves on the stretched string. So we want speed. So we know that speed equals to lambda times f, and we also know that frequency is given as 1 over the period. So v is going to be wavelength times 1 over t, which is lambda over t. So I'll substitute. What is the speed? I mean, what is the wavelength? What was the wavelength, not speed? I think the wavelength was 0.8. Yes, the wavelength was 0.8. So this is going to be 0.8. Then the period is given as 0.16, I think, 0.16 seconds. So I'll just divide this 0.8 divided by 0.16. So this is giving 5.0, or simply 5 because it's exact, meters per second. Then state Kirchhoff's first law. Normally we state Kirchhoff's laws wrongly, but the simplest way to state the first law is that the algebraic sum of currents at a junction is 0. Algebraic. Now also, as if you're a teacher, discourage your students from starting answers by saying Kirchhoff's first law states that. That's a wastage of time. So algebraic sum of currents at a junction is 0. The algebraic sum of currents at a junction is 0. When we say algebraic, it means you can say currents into the junction positive, currents out of the junction negative. That is what we mean by algebraic. One direction positive, one direction negative, into the junction positive, leaving negative. So when you sum up, you're considering the algebraic. Alternatively, you can say the sum of currents entering a junction, or the sum of currents entering a junction equals to the sum of currents leaving that junction. It should be the same junction you are considering. So the sum of currents entering a junction equals to the sum of currents leaving the same junction. Okay. A cell with internal resistance R is connected to two resistors of resistance R1 and R2 as shown in the figure. Okay, so they're in series. The potential difference across R1 is V1, so this is V1, and this is V2 respectively. The terminal PD across the cell is V. So the PD across the cell, that is the PD between this point and this point, is V. The current in the circuit is I. Use Kirchhoff's laws to show that total resistance RT of the external circuit is given by that expression. So I can start by Kirchhoff's second law by drawing in a loop. Let me draw in a loop that is from this point to that. Let the loop be anticlockwise. So I will say from Kirchhoff's second law, from Kirchhoff's second law, the terminal PdV should be equal to V1 plus V2. That is by Kirchhoff's second law. The terminal PD is going to be equal to V1 plus V2. Then, of course, from Ohm's law, if you know Ohm's law, we know that by Ohm's law, V equals to I times R. And remember, the current is the same. And the current is the same. So this is going to imply that where there is V, I'll put I times R. Where there is V1, I'll put I times R1. Where there is V2, I'll put I times R2. So it means I have I times R is equal to I into R1 plus R2. Then I will divide by I will divide by I both sides. So this cancels out, this cancels out. Hence, I have that R equals to R1 plus R2. So the two marks are just here and this substitution here. The EMF of the cell in the figure is 1.5. The values of R1 and R2 are 10 and 15 respectively. The terminal PD of the cell is 1.35 volts. Calculate the internal resistance R of the cell. Okay. So first of all, we know that total current in a circuit, I in a circuit is given by the EMF divided by total resistance. I'll write RT for total resistance. And of course, this is going to be the EMF is 1.5 divided by total resistance. They are resistors in series, so that is 10 plus 15. No, I don't think this is working. This is not total current. Let's say, okay, total current is going to be not EMF. This is going to be, because there is a current being supplied, this is going to be 1.35. So this is not going to be EMF. Because I'm not considering the internal resistance, so I can't use the EMF. So the total current here is going to be the terminal PD, which I'm going to call V over R in series, or over the external resistance R. So let me remove this. It is not total resistance. So this is going to be 1.35. So this is 1.35 divided by 25. So the current is 0.054 amperes. So that is the current I. I use the terminal PD because I don't know the internal resistance, so I didn't add the internal resistance here. If I know the internal resistance, then the current will be EMF over total resistance, which includes the internal resistance. So this is the current. So if I know this current, then it is now very easy because I know that the EMF is always equal to the terminal PD plus the velocity volts. Terminal PD plus the velocity volts. In other words, E is equal to terminal PD capital V plus the velocity volts. The velocity volts is the current times the internal resistance R. Because the same current through the fixed resistor is the same current through the battery, so it is the same current 0.054. So it means I times R, small r, is going to be the EMF, which is 1.5, minus the terminal speed, which is 1.35. So it means small r is going to be 1.5 minus 1.35 divided by the current I, which is 0.054. So 1.5 minus 1.35, then divide by 0.054. So this is giving me 2.7 recurring. So this is going to be 2.8 to two significant figures, 2.8 ohms. Alternatively, I could use potential dividers formula. Let me try to see if I can use potential divider formula. So for potential divider formula, the ratio of the resistances should be directly proportional to the ratio of the PDs. So R over the resistance in series should be equal to the lost volts over the terminal PD. That is the ratio of the resistances is equal to the ratio of the PDs. So R over small r over total resistance outside, which is 10 plus 15, should be equal to the lost volts, which is 1.5 minus 1.35, is equal to over the terminal PD, which is 1.35. So I have that R over 25 equals to, what is this? It's 0.15 over 1.35. So it means R is going to be 25 times 0.15 divided by 1.35. Let me check this. So 25 times 0.15 divided by 1.35. So it is the same thing, 2.8 ohms. So this is potential dividers. The ratio of the resistances is equal to the ratio of the PDs. Then a resistor of resistance R3 is added to the circuit in the figure so that the circuit is as shown in the figure. So we have added another resistor in parallel. Remember the effect of having resistors in parallel, total resistance decreases. So remember let's say this was 10, this was 15. Let's say they have added another one. Let's say I'll just use 10, another resistor. This one was 2.8. I'll round off to 3 for simplicity, for simple explanations. State and explain the effect, if any, of this change on the current in the cell. So initially, if we had no R3, initially I would say total resistance, I'll call it R initial, would be 10 plus 15 plus 3, which is, say, let's say it was 20, 10 plus 15, 25 plus 3, which is 28 initially. Then after, when we add another resistor, which is R3, so we shall have now 3 plus these ones 25 and 10. So it will be 25 times 10 over 25 plus 10 because they will be in parallel. So this would give me, I just want to give you a simpler explanation. That's why I'm doing this calculation here. So I have 25 times 10, 25 plus 10. Then I add 3. So this is giving us approximately 10. So this means total resistance here would be approximately 10 ohms when we add another resistor in series. Okay, so the total resistance has decreased. In other words, I just wanted to show you that total resistance decreases. So the total current in the battery through the battery, which is I total, is equal to the EMF divided by total resistance. Because total resistance has decreased, it means total current which goes through the battery must have increased. So it means the current in the cell increases. So I will say in my explanation, because there are 2 marks, I will say total resistance decreases. Total resistance decreases. And if total resistance decreases, it means total current in the cell will increase. So total current in the cell will increase. Let's see what happens to the terminal PD then. For terminal PD, I want you to remember EMF is equal to terminal PD plus the lost volts, or the PD in the internal resistance, which we call the lost volts many times. So it means terminal PD is equal to the EMF minus the lost volts. And remember, terminal PD will be equal to the EMF minus the lost volts is current, which is the current through the battery times the internal resistance. The EMF is not changing, the internal resistance is not changing, but the current through the battery has increased, which means the lost volts increases. If the lost volts increases, it means when I subtract it from the EMF, the balance becomes smaller. So the lost volts increases, which means the terminal PD decreases. So I'll simply say since the current is now greater, since current is now greater, the lost volts in bracket I will say PD across, or let me say PD on internal resistance, PD on internal, the PD on internal resistance increases. So the terminal PD decreases. So the terminal PD will decrease, as simple as that. Okay, I think this should be the last question because it is particle physics. Nuclei of course this is pro, nuclei of an isotope of copper Cu each have 29 protons and 37 neutrons. The isotope is a beta minus emitter. State the nuclide notation in the form of AXAZ for this nucleus of copper. So remember, A is the nuclear number, which is number of protons, 29, plus number of neutrons, which is 37. And I think this is 66. So I'll write this as A, not A, it is X. No, it is actually copper. So I'll write it C, U. Where there is Z, I put proton number, which is 29. And where there is A, I put nuclear number, which is 66. As simple as that. The energy spectrum of the beta minus radiation emitted by a sample of this isotope is shown. So a number of beta minus particles, and we see a continuous distribution of energy that confirms that this is really beta, because during any decay, the total energy is supposed to be constant. But if different beta particles have a range of energies, then then there should be other particles which are taking part of the energy. So the question is, use the figure to explain why other particles apart from beta minus must be emitted during this decay. So we know that the energy of any decay is supposed to be constant. So that's the first point. The energy of a decay, the energy of a decay is constant. The energy of a decay is constant. But the energies of beta particles that we are seeing, but the energies of beta particles have a continuous range of values as shown by the graph. So I'll say but the energies of beta particles, the energies of beta particles have a continuous range. Have a continuous range of values as shown by the graph. If the energy of any decay is supposed to be constant, yet the graph shows that the beta particles have a continuous range of values, then it means there are other particles which must be emitted that are taking part or that are sharing some of the energy. So I'll say, so other particles such as, because this was beta minus, other particles such as, of course, beta minus is always emitted by an antineutrino. So other particles such as antineutrino, the antineutrino must possess the extra energy, must possess the extra energy of the decay. So some of the energy must be taken or must be shared or is being shared by other particles such as the antineutrino. And lastly, state the name of other particles emitted during this decay. Of course, this is the antineutrino. If you want to be very specific, you can say the electron antineutrino. Oh, it's still continuing. The copper isotope decays to an isotope of zinc. Give the radioactive decay equation for this decay. Include the nucleon and proton numbers of all the particles involved. Since it gives us zinc and is a beta emitter, so I'll say copper, which is Cu 6629. It is giving us zinc. Remember, it is a beta minus emitter, so I'll say beta 0, -1. Of course, a beta minus particle is always accompanied by the electron antineutrino. So I'll write the electron antineutrino. I think I can write it like this. This one has no nucleon number, it has no proton number, but is the anti-electron neutrino. And I need just to consider or to balance the proton number and the nucleon number. So zinc will have a nucleon number will be 66. Then because I have to conserve proton number, this will be 30. So that 29 on the left and total 29 on the right hand side. So I think this is correct. Beta minus is accompanied by the antineutrino. This is the electron antineutrino. This E here is just show it is electron antineutrino. Yeah, I think I've used like 3 extra minutes because I gave more explanations. In case of any challenge, you can always write a comment. Until next time, bye bye.